Okay, hi everyone. Today we're going to work on finding probabilities involving the Central Limit Theorem. So we're going to spend a couple of minutes talking about applying the Central Limit Theorem and sampling distributions and finding mean and standard deviation. And then we're going to apply the Central Limit Theorem concept to finding probabilities using our Z-chart. All right, so let's take a look at the first couple examples. So here we have cell phone bills, residents Cincinnati have a mean of 64 and a standard deviation of 9. Okay, so there's a graph. Here you go. Distribution of cell phone bills. Kind of normal-like. I mean, it's not the best. I don't believe it is. So we have a random sample of 36 phone bills. Again, samples lots of times. We did 36 lots and lots of times. Drawn from the population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution, then sketch the graph of the sampling distribution. Okay, so we have to remember from our discussion about sampling distributions and sample means that the mean of the sampling distribution equals the mean of the population. Now, since our mean of our population is 64, then our mean of our sampling distribution is 64. Okay? Then it says, find the standard error of the mean. Now remember, standard error is the same as asking you, what is the standard deviation? So I'm interested in omega x bar. And we had a formula for that. That's omega over the square root of n. Okay, it gives us our standard deviation, which is 9. So we're going to do 9 over the square root of 36. Okay, so that's 9 divided by 6. And we get 1.5. Okay. All right, so we're going to sketch our new sampling distribution. So we're going to make a normal curve. Okay. Where our mean is at 64 and our standard deviation is 1.5 units. Okay, so if I wanted to write this number, I would write it as 65.5. Okay. All right, so as you take larger samples, this denominator is going to get bigger, which means our standard deviation is going to be smaller. All right, so let's try this again. All right, so we're going to do the same problem, except our sample size is now 100. We want to find the mean and the standard error of the mean of the sampling distribution. We're going to sketch it, and then we're going to take a look at what's the difference. All right, so the mean of the sampling distribution is still the mean of the population. Our population still has a mean of 64. So that is not going to change. The location of our mean is not going to change. But our standard deviation is now going to be 9 divided by the square root of 100, okay, which is 9 over 10, or 0.9. Notice the difference. Okay? Here, our standard deviation is 1.5. Here, our standard deviation is 9. So when I sketch our sampling distribution now, it is much thinner. Okay, that the distance from one standard deviation is 0.9. So this would be 64.9 instead of 65.5. So the larger the sampling, the smaller our standard deviation is going to be. Okay. All right, so let's try one more of these. Now here, population was not normal. We took a sample size bigger than 30. So we have assuming training heart rates of all 20-year-old athletes are normally distributed. So we're assuming that the population is normal to begin with a mean of 135 and a standard deviation of 18. Okay, so here's our graph. There we are. 135 is in the middle, standard deviation of 18 beats per minute. Random sample size 4 are drawn from the population, again, over and over and over and over again. So we definitely have a size that's definitely less than 30. Now, we can only do that because our population is normal to begin with. Find the mean and the standard deviation of the sampling distribution and sketch the graph. All right, so our mean is equal to the mean of the population, so that's 135. The standard deviation or the standard error, okay, was the standard deviation of 18 divided by the square root of 4. Okay, so 18 over 2, which is 9. Okay, so It's definitely smaller than what the normal distribution looks like to begin with, okay? So here we have 135. Here is a distance of 9. Okay, so this would be 144. Okay, notice that our, shall we say the height of our graph is thinner, okay? It's getting more pointy. All right, so that's how we're going to look at finding mean and standard deviation. All right, so let's look at finding probabilities. All right, so when we're finding probabilities, there's a big difference between what we were doing with our z-chart. We had the formula x minus mu over omega. Now, because we're taking sample sizes, we have a new z formula. Okay. That we're going to do the same process, okay? If it's less than, we're going to read the chart. Greater than, we're going to do 1 minus the chart. Between, we're going to subtract the two numbers on the chart. Okay, all of that's going to stay. Our process is going to stay the same. The only thing is that our z is going to be different. So we get a new z, okay, because we have a sample size. If we do not have a sample size, or our sample size is 1, then we're going to use the other one. Okay, so we're going to go z equals the mean minus mu x bar all over omega x bar. Okay, so this is our sample mean minus our sampling distribution mean over our standard deviation of the sampling distribution. You can also write it as x bar minus mu x bar all over omega over the square root of n. Okay, your choice. Okay, but because we're having sample sizes now other than 1, we're going to use this guy. All right, so let's take a look at a problem. So we have a figure here. Here we are. Of mean distances traveled by driver each day. You randomly select 50 drivers, ages 16 to 19. So we're only looking at this guy, 16 to 19. What is the probability that the mean distance traveled each day is between 19.4 and 22.5? And we're going to assume that the population standard deviation is 6.5 miles. All right, so what information do we have here? We have that the mean of our sample, okay, mean of our sampling distribution is 20.7 miles. Our omega x bar, we're going to have to figure that out, is 6.5 divided by the square root of 50, which is 0.92. Okay? All right, so our sample size here is 50. That's how I know I have to use the formula we just went over. Okay, so everything else is staying the same. So we're going to be interested in finding the probability that we're going to be between 19.4 and 22.5. Notation is going to be different. Instead of having x in the middle, I have x bar. So we're still going to have to find the z minus 20.7. Okay, and I'm going to put my omega x bar here, which was 9.92. Okay, when I did the math, I got 1.41 for that one. And then we're going to do the same thing over with the 22.5. And I got 1.96. Oh, this guy's negative, sorry. All right, so we're going to find a z. Negative 1.41 less than z less than 1.96. Okay, remember we're converting to a z so we can use our chart. All right, so I got to go to my standard normal chart, my z chart. Okay, and I have to find negative 1. I'm already on positive 1.96. So let's find that first. 1.96, 0.975. Okay, because we're always going to take the larger minus the smaller. Okay, and then negative 1.41. 0.0793. Okay, subtract them, and that's going to be 0.8957. So we could say that 89.6% probability that drivers between 16 and 19 travel between 19.4 and 22.5 miles. Okay, so let's try another one. Okay, again, the key is looking at, do we have a sample size? All right, so we have a mean room and board expense for four-year colleges is about $10,453. We randomly select 9 four-year colleges, and we have a probability that the mean is less than that. Excuse me. Now, 10,750. We're going to assume that room and board expenses are normally distributed and has a standard deviation of 1,650. Okay. So again, I just want to write myself notes here. Mean of X bar is 10,453. Omega X bar is going to be 1650 divided by the square root of 9, which I got 550 when I did that. Okay? All right, so let's find the probability that we're less than 10,750. We're going to have to convert that to a z. All over 550. Okay, do the math. I got 0.54. Okay, we're going to find the probability that the z is less than 0.54. Okay, if you feel like you need to make a graph or draw a picture to help you, feel free to do that. Okay, so we're going to go to 0.54. I got 0.7054. Okay, and again, we can say now that in this particular case, we have that the probability that we're going to pay less than $10,750 is about 71% or 70.5%. All right, let's try this last one. All right, some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed. Okay, so we're going to say it's normal to start with a mean of 1615 and a standard deviation of 550. What is the probability that a randomly selected college student who uses a credit card to pay for college-rated expenses pays less than $1,400? Notice one randomly selected college student. Okay, so our sample size here is 1, so we don't need to divide by the square root z, but if you wanted to, you could make it the square root of 1. It's your choice. Okay, so we want to be less than 1,400. Okay, notice I'm using not X bar there, but just X. Okay. So I'm going to convert that to a Z. Notice my denominator is just $550. Okay, I got negative 0.39. So we're finding the probability that Z is less than negative 0.39. Negative 0.39. Okay, let's find 9. It's over here. 0.3483. Okay, so the probability of a single college student is about 35%. All right, so we're going to randomly now select 25 college students who use credit cards to pay for school-related expenses. What is their mean amount? Is it less than 1,400? So is there a difference between a single person and a sample of 25? So we're finding the probability of X bar being less than 1,400. Okay, converted to a Z. Oh, wait, before I do that. We have a different standard deviation. Our mu of X bar is still 1615. But now we have omega X bar, which would be 550 over the square root of 25. Okay, so we have a different omega here, which is 110. So when I convert this to a Z, 1400 minus 1615. This is now over 110, not 550. So we get a different z-score now of negative 1.95. Okay. So we're going to find the probability that z is less than negative 1.95. Okay, look that up. Negative 1.9. Okay, 5 is here. So 0.2056. Oh, 0, 2, 5. Whoa, let's try that again. 0, 2, 5, 6. So our probability goes from 35% to 3% by taking a sample size. So there's a huge difference in our probabilities. So when we compare the two, what happens is that because we have a sample size, okay, so because there's a sample size and a smaller standard deviation, the probability becomes smaller. All right, please let me know if you have any questions, guys. And again, remember that we're going to be staying in, stay safe. Talk to you later.